Okay. Hi guys. Uh, there's so much confusion. I'm sorry, it became a little late. Right. We'll try to start it right away. Right. Okay. So, so you're saying, if you can remember, we have completed your isomedicine. Is everyone ready? People, are you ready? Obviously, you'll be ready. You'll be waiting for so long time, right? Uh, yeah. Okay. Cool. So yeah, so as I discussed, right? So we have completed isomedicine, right? And I started dealing with intermediates, if you can remember, right? Last class, right? So what happened there? I told you that whenever a bond breaking happens in organic, right? So it can happen in two ways, right? So one is homolytic cleavage, the other one is heterolytic cleavage, right? So when I told you homolytic cleavage happens, I told you that you should be using an half arrow mark, right? So something like this or something like this, right? So this is how you represent the half arrow mark. So this indicates that wherever the electron came from, the parent atom, it is going to go to that parent atom itself, ending up with free radicals, right? And whenever you have a heterolytic cleavage, basically the shared pair of electron is going to go to one of the atom. Again, it depends on the electronegativity, but sometimes some other factors also, right? So for example, if CCl bond is there and it breaks, right? So you will have say Cl will take the electrons, will form Cl minus, and I'm going to form carbocations, right? In this case, carbon loses electron, right? And when I go for carbanions, how it is forming, obviously the electron pair is going to be taken up by the carbon, right? So basically, whenever molecules containing H plus, right? When the H plus comes from carbon atom, so in that case, you will be using carbanions there, right? So yeah, these are the broad three examples of intermediates, right? So what else? So what are the other intermediates you have to know, right? I told you there are two or three special intermediates which you'll not be seeing them frequently here in chemistry, organic chemistry, but yeah, they are little important. So we'll look at them, right? So I have the next intermediate to be carbene. Okay. Guys, hope you're able to, please give me yes if you're able to hear me, because I just want
Yes,
to
sir.
confirm that you're able to hear.
Yes,
Cool.
sir.
Thank you.
Yes,
Right.
sir.
Yeah. Okay, thanks. Right. So the next intermediate is carbene. And guys, one more thing. Uh, can I continue this class till 9 o'clock? If do you have school today? Is it okay or what?
Um,
Do you have if you have some other job or if you have school, we
we
can wind
have
it up and say you have
exams on Monday, sir.
exams on Monday. Okay. So then, so maybe 1 hour, like this 1 hour, maybe 1 hour, I'll give you a compensation class, right, for all the things happen, right? So we'll plan something like that. So today I'll finish it by let's say 8:30, 8:40 max. I'll finish it. Okay, fine. So next intermediate is carbene, right? So this is a special intermediate, right? So we'll look at the structure of carbene first. Okay. So I know carbon atom is going to have 4 electrons in its valence shell, right? So now this is how the structure is going to be. Say I can have two atoms, like say two hydrogens like this, right? And I'm going to have two electrons like this, right? Now, now I don't know whether like you should have studied in your chemical bonding chapter in your 11th, right? So whenever you have this kind of things happening, it is this particular electrons are going to be called as lone pairs, isn't it? Whenever I have non-bonding electrons present. Non-bonding in the sense the electrons which are there in the valence shell, right? But it is not taking part in the bonding, right? So those are what are called as non-bonding electrons, right? So generally we see non-bonding electrons will be of the form of lone pairs only, right? Or I can have radicals. Like say I can have one single electron, as you see in free radicals. That is also a non-bonded electron. Right. But in this case, in case of carbenes, you are not going to call that as lone pair. right? Because they are not paired actually. If it's going to be paired, it should be like this. Hope you understand what I'm telling, right? If it is going to be a lone pair in a single orbital, it should be paired like this. Okay, but here in carbene, no, this is not how it's arranged, right? It is basically going to be arranged maybe like this. Okay, this is how it is going to be arranged here. This two electrons. This is how it is arranged, right? So I cannot call them as lone pairs. So how should I call them? Right? I should call them as diradicals. Right? I know monoradical will have one unpaired electron. Right? So these are the examples of diradicals. And diradicals, sorry, diradicals are going to have two unpaired electrons. Okay, one electron paired, unpaired, another electron unpaired separately. So this is what is called as my carbene. Okay, right? So I can have so many types of carbene. This is two hydrogen atom. I can even have, this is called methyl carbene. I can call it as methyl carbene, or I can even have dichlorocarbene. I think from the name itself, you'll be able to understand CCl2 double dot, right? So this is my dichlorocarbene, right? Fine. So we hope you understand what carbene is, right? Carbene is going to be a diradical. That's it, as simple as that, right? So where and all you will be using them, right? I told you carbene is the intermediate in your Reimer-Teyman reaction, right? I hope you remember what I said, right? You might not know what is the mechanism of Reimer-Teyman reaction. Everybody has studied what is Reimer-Teyman reaction? Reimer-Teyman reaction. In aldehydes and ketones, it is going to come. So if you can remember, maybe I can write the reaction here, then you might understand what is Reimer-Teyman. So if I have phenol, right, and if I go for KOH, KOH in the presence of CHCl3, chloroform, right? So you will see that I'm going to get a salicyl aldehyde. This is what salicyl aldehyde, right? And instead of a chloroform, if I put CCl4, I'll be ending up with COOH instead of CHO, right? Okay, so it's very simple. If you can understand how the reaction proceeds, right? So what is going to happen, I'll tell you, right? So this KOH and CHCl3, right? I would say first the OH minus is going to come from the KOH, right? So what is going to happen is this hydrogen which I have here, right? CHCl3, hydrogen which I have here is going to go out. It is going to form H2O with this OH minus, right? So what will be remaining? I'll be having CCl2 minus. Okay. Now CCl2 minus will be there, right? Now this CCl2 minus, am I doing it correctly? Oh, it's CHCl3. I'm sorry, people. Okay, that's why it's coming wrong. So it's CCl3 minus will be there, right? So what I do is I remove a Cl minus. Okay, so initially I had OH minus and chloroform, right? So OH minus is a base, so it can take up the proton, right? OH minus is a base, so it can take up the proton. So I'll end up with CHCl3, right? So this CHCl3 will lose a Cl minus, right? So what will you have then? CCl2 double dot. That is my carbene. Okay, and obviously this carbene will go attack the benzene ring. Then you will have something like this. Something like this will come. So two chlorine atoms will be there, and this chlorine atoms will undergo hydrolysis, right? Hydrolysis in the sense these two chlorine atoms will be converted to OH. Okay, and I don't know whether you know this. Two OH groups in the same carbon atom is unstable. Okay, two OH groups on the same carbon atom is unstable. You cannot have that, right? So as soon as it forms two OH groups on the same carbon atom, what is going to happen is I am going to remove a water molecule, right? I'm going to remove a water molecule. H from this, OH from this, you remove it. So what will be ending up is with this. Okay. So don't worry, people. If you don't understand the mechanism, it's very. I will again see it. Don't worry, right? But what I'm telling you is that in this reaction, dichlorocarbene is the intermediate. Okay, right? Fine. So there are other reactions also where you will be having carbene coming, right? So carbene is generally used in your addition reactions. So when I have a C double bond C, right? So any questions here, people, from the mechanism of how the reaction happens? What is carbene? Any questions?
No, sir.
Okay, so we'll move on. Okay, so when I have a C double bond C, right? So generally I know I can add HCl to this, Cl2 to this. So many types of addition reactions are possible. I can break the one of the double bond and I can make two other bonds along with carbon. So that is there. So when I have a carbene coming with this, say I put CH2, right? A carbene. I'll tell you how to prepare a carbene. That we'll see later. Again, we are not going to see it now. We'll see it when we go for this kind of reactions, right? Right. So if I have what is that carbene coming, so what is going to happen is, so you can see that say I have uh, diradical here. Now if I break this, I would say this bond is going to be broken and you are going to have this kind of interaction come. Okay, that pi bond is broken. So if the pi bond is broken, say I have I form one radical here, another radical here, right? And this electron, this electron, this electron, this electron are going to interact. So what will you form is carbon, carbon with having this, and I'm going to have CH2. This is what is going to get formed. Always you'll end up with a cyclopropyl group, right? So whenever you have a C double bond C, right, and you're going to add it to a carbene, right, you will always end up with cyclopropyl group. It might or might not be the main chain, but again, you will eventually see a cyclopropyl group, right? So like I can tell you one way of preparing this carbenes. Say for example, if I have CH2Cl2, okay, if I have CH2Cl2, if I heat it with zinc, okay, if I heat it with zinc, zinc I know will form ZnCl2. Very simple, right? Zinc I know will form ZnCl2. So what is remaining is my carbon. Okay, right? So these are the this is one of the ways. There are so many ways of preparing carbene, but we don't have to go into it, right? So carbene is there. You know how it will react, and you will understood what exactly is the carbene, right? Okay. So other than this, I have something called as nitrines, right? So nitrines are very simple. But uh, I don't think you need it, but I can just tell you, right? So nitrines are something like this. Nitrines, I will have, I think it's going to be C double bond N with, yeah. So this is my nitrines. Okay. So, and I also have something called as ketenes. Anyways, like this is not important to you people. Nitrines, ketenes, carbene is the only important thing, right? So if someone asks you, what are the intermediates you know, right? What are the intermediates in organic chemistry you know? You should be telling them that I have free radicals, carbocations, carbanions, carbenes, nitrines, ketenes, right? So all these things are the different kinds of intermediates available in organic chemistry, right? Okay, now that we understood what are all the intermediates, right? The next step, right? The next step is to understand which will be more stable, right? Which will be more stable. I mean, in the sense, I'm not telling that carbocations are more stable than carbanions or free radicals are more stable than carbocations. No, I'm not telling that. If I have a carbocation, say I know that in a chemical reaction, right, in an organic reaction, carbocation is the intermediate. Okay, right. Now, there can be possibilities that more than one type of carbocation can be formed, right? More than one type of carbocation can be formed, right? So in that case, you have to decide, okay, I have two types of carbocation getting formed. So obviously, if you look at the product, right? If you look at the product, say like if at all you have two carbocations formed, there should be two different products, isn't it? Right? So definitely, if two different products are there, one of them will be majority, right? One of them will be say 100%, 80% will be one of them, 20% will be another product, right? Indicating that this is the major product, whereas the first one is the major product, second one is the minor product, right? So depending on what is the major product is, right? You'll be able to actually decide which is the carbocation predominantly formed in the chemical reaction. That is one thing. The second thing is, why is it that that carbocation only is formed and not the other one? Basically, why is it formed in more amount, and why the other carbocation is formed in less amounts? That you will be able to decide based on stability, right? Obviously, the more stable carbocation, right? The more stable carbocation will be formed in majority, and the less stable carbocation will be formed in minority, and accordingly, the product formation also occurs, right? So for this, I can give you a very simple example, right? So you know Markovnikov's rule, isn't it? Right? So like I can go for it. Say if I have this and I put HBr, right? So I know the Br atom should come here only, is it not? So the product would be this. At least the major product. Minor product would be Br atom having here, isn't it? Right? So what we have to understand is, if I can understand the mechanism, right? I don't even have to know what is Markovnikov's rule. Like there is no, actually Markovnikov's rule is derived from the mechanism, because I know carbocations are going to get formed, right? So I don't even want to know what is Markovnikov's rule, right? I can actually answer the question by knowing the mechanism, why this is the major product, right? So Markovnikov's rule says that the nucleophile should get attached to a carbon atom which is more substituted, right? The nucleophile in this case, oh wait, we didn't talk about that. So nucleophile is known as having a negative charge. Okay, we'll speak about it, nucleophile, electrophile, right? So in this case, H plus, which is having the positive charge, is my electrophile. Electro is negative, phile is loving, electron loving species. So definitely there should be positive charges. And obviously Br minus. Anyways, right? So now if I look at the mechanism, right? Now if I look at the mechanism, what is going to happen is, so I have CH3 double bond. First the H plus comes. Okay, first the H plus comes. So obviously the H plus have two site of attacks, right? So either it can attack this carbon or it can attack this carbon, right? Okay. So which like both things can happen, but again, one of them is going to be more stable, other one is going to get the other one is going to be less stable, right? So if this what to say, if this H plus attacks this carbon atom, right? So what is going to happen? This pi cloud is going to move here, make a negative first. Like let me go step by step. The pi cloud here is going to break heterolytic cleavage to form a carbanion, not carbanion. You will not even see that. So because the H plus is coming, the pi bond breaks, and you will see that. So okay. So if this undergoes heterolytic cleavage, right, and this carbon atom attains negative charge, definitely this carbon atom should get a positive charge. Is it not? This carbon atom negative charge, but that is neutralized by the H plus, right? And this carbon atom is going to get a positive charge, right? So you will have CH3, CH plus CH3. So the hydrogen plus attack here, the pi bond is broken, and you will get a positive charge here, right? Now this is one of the possibilities. What are the other possibilities? Now the H plus can attack this one, this carbon atom. In this case, how the pi bond is going to break? The pi bond is going to break this side, making a negative charge that is neutralized by the H plus, and this carbon atom, the last carbon atom, will get a positive charge. So you will see that CH2, CH3 plus. This is the other carbocation which is getting formed, right? Only two possibilities, right? Now, obviously, you can see from the Markovnikov rule, this is the final major product. So definitely, this carbocation is the one which should have been in majority, right? This carbocation should have been formed in majority, and this carbocation, the second carbocation, is not formed much, right? Again, what is the reason? The reason is going to be because of stability, right? So here you can see, I hope you know what is primary, secondary, and tertiary, right? So in this case, it's a secondary carbocation. In this case, it's a primary carbocation. So definitely, secondary carbocation is more stable than a primary carbocation. So that's why secondary carbocation is formed in majority, and accordingly, the product is also formed. Okay, now this is a very simple reaction, right? Say, I can have a reaction where I can have, say, at least 5 types or 6 types of carbocations getting formed, right? So you must be in a position to understand, okay, these are the carbocations formed. So you have to know, right? How do you put them in the order of stability, and accordingly you will be able to predict what will be the product. Okay, right? So for us to understand how do we determine the stabilities and all that, so we have to know certain things. There are a lot of tools in organic chemistry, right? There are a lot of ways in which you will be able to decide the stability. Okay, this is less stable, this is more stable. Not only for carbocations, for carbanions, free radicals, for everything, we'll be able to do that. Okay, so we will see what are the ways by which secondary is most. Now in this case, you saw that secondary is more stable than primary, but you might not know why, right? So all these things we'll see it now, right? Okay, so I'm gonna see this electron displacement effects, right? Electron displacement effects. Okay, so obviously from the name itself, we can see that the electron is not going to be there at one position. It is going to be continuously moving, right? So there are so many effects based on this. Among that, the first one, you should have known it, is what is called as my inductive effect, right? So inductive effect, okay. So for this effect to happen, right? For this effect to happen, I should have a polar bond. So the main requirement for inductive effect to happen is that I should have a bond which is polar. Okay, the next question is, what is being polar? You tell me what is being polar.
Having two opposite quantities.
Having two opposite quantities. Okay, I understand. So you're talking about two oppositely
No, in
charges
this
in this
case,
case.
charges. Yeah.
Yeah, correct. Right. So how do you think I can have two separate charges? I mean, in the sense, opposite charges.
If there's a difference in negativity between the atoms.
Very good. Right. So definitely, for example, if there is a bond, right? For example, a HCl bond, if you take, this is not an organic compound, but still, I'm just giving you an example, right? So if I take HCl, for example, right? So you will know that chlorine atom is highly, excuse me, right? So chlorine atom is highly electronegative, hydrogen atom is highly electropositive, or I would say very less electronegative. So now what is going to happen because of that? Say if I consider this with my HH bond, right? In this case, both the hydrogen atoms, I would say, are equally electronegative, right? So it's all about where the electron cloud density is maximum, right? So you see that the electron pair is shared here. There is a covalent bond formed. Now, if you see, where is the electron density maximum, right? Where is the electron density maximum? The electron density is going to be maximum at the center of these two nuclei, right? These two nuclei is going to be there. At the center of this nuclei, you will see that the electron density is maximum. Okay, right? Fine. Now, in this case, it is definitely not going to be like this, right? Because they are not equally electronegative. Or in this case, I can tell that this is pulling electron from this side, this is pulling electron from this side, and the force which they pull is same, because both these are same atoms with same electronegativity, right? But in this case, since chlorine is more electronegative, it is going to pull the electron cloud more towards itself, and the electron cloud is going to move away from hydrogen. So definitely, the electron cloud is not going to be at the center. The electron cloud is going to be more towards chlorine and less and more far away from hydrogen. So because of this, right? Because of this, what is going to happen? right? So in this case, since the electron cloud is exactly at the center, there is no separation of charges happening, right? But since here the electron cloud is more towards chlorine, right? I am going to have chlorine to have a partial negative charge, not full negative charge. Chlorine is not taking up the electron. It is just that the electron cloud is moving more towards chlorine, right? So this will induce, right, because of the movement of electron, right? Chlorine is now in this case is neutral because the bond has been formed, right? But since the electron cloud is a negative charge is moving towards you, it's like having a good friend and a bad friend, right? So obviously you are neutral. You have no this thing. You are not neither good not bad nor bad, right? But if you have a good friend, maybe all your good qualities will improve. If you have a bad friend, all your bad qualities will improve. It's all about who's close to you, right? So in this case, electrons are close to chlorine, so that will induce, right, a partial negative charge on chlorine, and obviously there will be a partial positive charge on hydrogen, because say I had a bad friend and we had a fight and he left me, so definitely all my good qualities will start improving. So that is my partial, again not fully, right? The effect will still be there, right? Okay, so there will be a partial positive charge on hydrogen. So this exactly is what is the polar bond. Okay, I can even mark it here, right? So this exactly is what is called as my polar bond. Whenever you have charge separations happening, okay, whenever you have charge separations happening, and obviously for a charge separation to happen, you need to have a polar bond, right? So this exactly is what is called as a polar bond. So this is the first requirement for inductive effect to happen, right? So we'll try to understand this. Right. So for you to understand inductive effect, you have to understand that there can be two types of groups in organic chemistry, right? Two kinds of groups, right? So what are these? I have something called as electron withdrawing group, EWG. EWG means electron withdrawing group. Okay, and I have something called as electron donating groups, right? EDG. EDG is electron donating groups. EWG is electron withdrawing groups. Okay, so first you have to understand this, right? Or actually, like before we see this, I can actually tell you what inductive effect is. Say for example, people, I have CH3, CH2, CH2, Cl. I have that, right? So what is going to happen is, say now, if I look at where and all I have polar bonds, you can tell that so CH is a polar bond. Okay, yeah, because electronegativity difference is there. I'm not denying, right? But there are certain scales which we use. Okay, so the scale is, if at all you want to call the bond to be polar bond, right? If at all you want to call the bond a polar bond, the electronegativity difference between the bonding atoms should at least be greater than 0.7. Okay, so anyways, if you want, you can remember this. Anyway, you'll be seeing this in chemical bonding again, right? So what I'm telling is, if you want to call the bond a polar bond, right, the difference electronegativity, that's why I wrote delta n, delta en, right, should be greater than 0.7. So CH bond does not come under this category. CCl bond, yes, it comes under this category. Okay, so yeah, so definitely the polar bond which I have here is going to be this CCl bond. Okay, so same thing what happened here can happen here also, right? So now obviously since the electron cloud is going to move towards chlorine, so making it have a partial negative charge, and obviously since carbon atom, the electron cloud is moving away from carbon atom, it is going to have a partial positive charge, right? Now it is not going to stop here. Okay, so what is going to happen is this carbon, right, this carbon which has the electron cloud has moved away from this is deficit of electron, right? It is not having much electron density around it. So what is going to happen? And you can also see that there is a positive charge, I mean a partial positive charge. So what is going to happen is this electron cloud which I have here, right, is also going to get shifted, just to make sure that this carbon atom is satisfied. Such a greedy carbon atom, not greedy because of itself, right, because of the chlorine, but still, right, just to satisfy the electron density of this carbon, right? So what is going to happen is the electron cloud is going to move towards this, right? Or in other words, how you can visualize it is, the carbon atom is, sorry, the chlorine atom is so highly electronegative that it not only affects the first bond, it affects the second bond also. So this also is going to move towards fluorine. Or what I said in the first case, this carbon atom is electron deficit. So if for it to get satisfied, so the electron cloud again moves. But again, how much electron cloud moved here? It is going to be high movement. It is going to be a large movement towards fluorine. That much movement you will not see here. Very slightly, maybe the electron cloud is going to move, right? So obviously, the charge is going to get induced here. Why do I say is induced? Because of this, because of this, because of this. So someone is inducing in the sense, what to say? Uh, what I have some characteristics, because you be with me, those characteristics come to you also. So I'm the one who's inducing, and you are the one who are getting induced, right? So what is going to happen? So because the electron moment is not going to happen that much, say, pronounced as in the last case, so this will have a lesser partial positive charge. So I put del positive, indicating that it is going to be, the positive charge is going to be lesser in magnitude compared to this carbon atom's partial positive charge, right? Okay, now what about this carbon? This carbon also will have, but it will have still lesser, right? So if you go for about like 3-4 carbon atoms away, the charges will become zero. It is not, it is very negligible. Okay, so this is what is inductive effect, right? So because of the floral, there will be a charge separation happening, right? And that is going to affect the other bonds also. Okay, fine. Now, people, now you see that the fluorine atom is here, right? So obviously, what you can understand from this is that the first carbon atom is having a very high charge, second carbon atom little lesser, third carbon atom very less, right? So what you have to understand is inductive effect is actually distance dependent, right? It is actually going to be distance dependent. What do you mean distance dependent? So for example, instead of having this carbon atom, if I have this fluorine atom here, right? So definitely now which carbon atom would have the highest positive charge? This carbon atom would have the highest positive charge, and these two carbon atoms almost will have equal amount of positive charge, but still lesser than this, right? So lesser than, I mean, these two will have some positive charge, but lesser than this. But these two carbon atoms will have equal positive charges, equal magnitude of positive charges, right? So obviously, where that particular atom is present, the distance between that particular concerned carbon and whatever I'm say the heteroatom in the sense other than carbon and hydrogen, whatever the other atoms you have are what are called as heteroatoms, right? So the position of the heteroatom, distance between the heteroatom and the carbon of my concern, it can be of any of these carbon atoms, right? So carbon atom of the concern, all those things matters for your inductive effect. Okay, fine. So all this we started for deciding your stabilities of intermediates, right? But it is inductive effect is not only used in that, right? So in organic chemistry, I have so many different kinds of acids, bases, and all these things, right? So inductive effect can also be used to determine, say, if I give you 2 carboxylic acids, right? So you will be in a position to understand, okay, this is more acidic, this is less acidic, the pH of this is higher, the pH of this is lesser. All these things you'll be able to predict with the help of inductive effect. But for now, we will we will restrict our discussion only to intermediates. Then again we'll go for the acidic strengths and basic strengths, right? Okay, so this we understood. So I told you inductive effect can be produced, right? Inductive effect can be produced by 2 kinds of groups, right? So first kind of groups are what are electron withdrawing groups. So what you saw here, chlorine is doing what? Chlorine is actually withdrawing electron from carbon, right? Right. So whenever you see that highly electronegative elements or highly electronegative like OH, even I say NO2, all these things, right? All these things are going to be electron withdrawing groups. Okay. So examples of electron withdrawing group, all halogens, right? OH, OCOR, right? NO, maybe carbonyl, no, right? So what else? The NO2, right? So all these things, right? All NO2, NO2, you would have studied in benzene mechanisms. That NO2 is an electron donating group. That is by resonance. Okay, we'll come back to that. Okay. So for now, nitrogen is highly electronegative, so it will be able to pull the electron towards itself. That's what you need to understand. Okay. And electron donating groups, right? So mostly you will have all alkyl groups, right? All alkyl groups will actually be electron donating in nature, right? Say for example, ethyl group, propyl group, cyclohexyl group, cyclopentyl group, all these alkyl groups. Now, first thing, how do you define an alkyl group? Alkyl group can be defined as this, right? It is going to have one hydrogen atom less than the corresponding alkane. CH4 is methane, CH3 is methyl group, C2H6 is ethane, C2H5 is ethyl group. So alkyl groups will have one hydrogen atom less compared to the parent alkane. Okay, so all alkyl groups are going to be electron donating in nature, right? And the next question is, sir, which one would be more electron donating? Say if I have CH3 and C2H5, right? Which will be more electron donating? I would say there is not going to be much difference, right? But still strictly speaking, I would say that C2H5 is going to be more electron donating than CH3, right? So I can even write it here. C2H5 is going to be more electron donating than CH3. Obviously, propyl group will be more electron donating. But again, you cannot use this, right? Whatever I'm telling you here, right? This is not a very good tool to use when you're going to decide stabilities, or say if you're going to go for acidic and basic strengths. This is really not a good tool. But what you have to understand is all the alkyl groups are going to be electron donating in nature, right? So whenever these kind of situations comes, right, C2H5 and the CH3 is there, there are other methods, other effects which is going to help us do it. Okay, so for now you don't have to worry, right? Cool. So what you have to understand is electron withdrawing groups, electron donating groups, right? So you have understood it's all with respect to carbon atom. If the group is capable of removing electron, or say withdrawing electron from carbon, it is called electron withdrawing. And if it is able to donate electron to carbon, it is called electron donating groups. And obviously, since I have two different kinds of groups, I can have two different kinds of inductive effects, right? So remember, electron withdrawing group will cause me minus I effect. Okay. Now, why I put a minus sign, right? Again, I told you it's all with respect to carbon atom, right? So electron withdrawing groups are going to decrease the electron density on carbon, right? So that's why I call it as a minus I effect. Again, I repeat, electron withdrawing groups are going to decrease the electron density on carbon, right? So therefore, I give the name minus I effect. And obviously, electron donating groups will give me plus I effect because they are going to increase the electron density on the carbon, right? So it's all with respect to carbon atom only. But the carbon is having a decreased electron density, minus I, increase in electron density, plus I. And obviously, EWGs and EDGs will cause minus I and plus I effects respectively. Okay, right? Fine. So this we understood the basis of inductive effect. Now we'll try to understand how do you use this to decide the stabilities, right? Actually, actually, I'll be able to include your acidic and basic strengths also here because I don't want to take it separately. But again, this is not the only way by which we'll be able to speak about this stability of intermediates, or in the case that I have to talk about the acidic and basic strengths. But still, in the under inductive effect, whatever comes, I can complete it. Right? Fine. Cool. So we'll go for it. First, we'll talk about the intermediates. Right. Say I take now. Please understand, people. Right. Whenever we talk about intermediate stability, we don't actually take carbene's stability on into picture. It is too much higher level. It is not required for you. If you want, if you're interested, yes, I can teach you, but it is really not required for you. There are already so many other things which you have to remember, right? Okay, so we will be taking only carbocations, carbanions, and free radicals in our discussion. Okay, and especially in this discussion, that is in my inductive effect discussion, please understand that if you want to decide the stability of an intermediate through inductive effect, right, that particular intermediate should be charged. That's the condition, right? So what I'm indirectly telling you is that you cannot use inductive effect for what? You can use inductive effect for?
Polar bonds.
No. I told you, right? Now, what is the statement I told you? I told you, if you want to decide the stability using inductive effect for an intermediate, right? So I'm telling the intermediate should be charged. Okay. So what kind of intermediates I'll be able to use here to deciding stability?
Free radicals.
Now, please understand, I'm telling, right? I'm telling you that if you want to decide the stability by using inductive effect for an intermediate, right? That intermediate should be charged. If it is uncharged, I will not be able to decide the stability. So which I can use here? Tell me.
Carbocation and carbanion.
Exactly, right? So carbocations and carbanions are the ones which are charged, right? Only for those two things, I will be able to use inductive effect. For free radicals, I cannot use inductive effect because it is not charged. We can see that, sir, one single electron is there, but that is not a charge. That is one single electron. It is neutral. Okay, free radicals are neutral, and your carbocations or carbanions are charged, and even your carbene is neutral. Okay, right, fine. So we will try to do this, right? So let me take some okay, before this, hope everybody knows that I have three different kinds of intermediates. Not three different, I have so many types of intermediates, again, for a particular carbocation or carbanion, right? So I can have a primary, secondary, tertiary carbocation. I can have a benzyl carbocation. I can have an allyl carbocation. So again, so the same things will come in free radicals and your uh, carbanions also. Right? So hope you know all these things, right? So if you want, I can tell you. Well, let me take the example of primary, secondary, and tertiary, right? Say if I say primary, for example, this is primary carbocation with a positive charge. Now, how do you decide this? Right? So I decide this based on the carbon containing the charge or carbon containing the radical, right, is attached to how many other carbon atoms. Okay, is attached to how many other carbon atoms. So if you see that, right, the carbon containing the charge is attached only to one of the carbon atoms, right, then it is going to be called as primary. In this case, you see that the carbon atom having the charge is attached to one other carbon atom only, so it is going to be primary, right? And obviously secondary will be attached to two carbon atoms, tertiary will be attached to four carbon atoms, sorry, three carbon atoms. Okay, so this is my primary, and this, say if I talk about secondary, and so this is my secondary, and tertiary, something like this. Okay, fine. Now I am going to decide which is more stable, which is less stable with the help of inductive effect. Okay, fine. Now please understand, people, if you want to have stability, right, if you want to have stability, right, what you have to understand is more and more neutral substances are stable compared to charged substances. Is it not? So obviously, if I compare HCl in the molecular form, or if I consider it in the form of H plus and Cl minus, definitely the molecular form is more stable, right? So definitely charged species are unstable generally, and neutral species are more stable. This is the first thing which I have to understand, right? And so if at all I have two charged species itself, right? If now we'll not go for two neutral molecules because there are so many other parameters, bond strengths, and all these things will come. But for now, we will restrict the discussion to if I have two charged molecules, two charged particles, right? So in that case, how will you decide the stability? Now, obviously, the one which is having lesser charge is more stable, because when I say where I have lesser charge, it is more towards the neutral side. Is it not? Right? So what you have to understand is, people, stability and charge are going to be inversely related. Less charge, more stability. More charge, less stability. So with respect to inductive effect, or to so many other things, not only to inductive effect, you will see that stability is going to be inversely related to the charge. Okay, Now, we have seen so many things, right? And we have seen this also. Now, combining all this, right? Can you tell me what will be the order of the carbocation stability? Tertiary, secondary, primary is there. Primary, secondary, tertiary is there, right? Now, you tell me what will be the order of stability and why is that? You tell me from what I have learned till now.
It will be tertiary, secondary, and then primary.
Okay, ma'am. Why is it like that?
Because for the tertiary, we have three plus I groups.
Okay, through three alkyl groups, and so
So they'll give you a plus I effect and it will neutralize the charge.
good, very good, right? So we already know this. I told you that your alkyl groups, right? Your alkyl groups are going to be electron donating in nature, as she said. They are going to cause plus I effect, is it not? So what you see here is that there is only one methyl group which is going to donate electron, and by thereby donating electron, what will happen to the positive charge? Positive charge will decrease, right? The amount of positive charge here would have decreased because this is going to be an electron donating group, right? And obviously, in this case also, there are going to be two electron donating groups, decreasing the positive charge. So definitely, if I compare the amount of positive charge here and the amount of positive charge here I'm going to have lesser positive charge, right? And in this case, definitely, I have three electron donating groups, decreasing the positive charge. So obviously, the least amount of positive charge would be here, then here, then here. So then I can easily say that this is the order of stability. Okay, this is the order of stability. Tertiary is more stable because I have three electron donating groups, decreasing the positive charge. Secondary is having two, and primary is having only one electron donating group. So primary will have the highest charge, and tertiary will have the lowest charge, and vice versa will be the stability. Okay, right? Fine. So if I remove them to become a carbanion, now what do you think will happen? Alkyl groups are still electron donating in nature only, right? Now, if they're electron donating in nature, and if I see that there is a carbanion, so definitely the amount of negative charge will
Increase.
yes, right? So the amount of negative charge will increase, thereby it is going to destabilize this, right? So I can say that this is the thing for carbocations, but for carbanions, it will be exactly opposite. Primary will be more stable than secondary. Secondary will be more stable than primary, and this would have been for my carbanions. Okay, so now we have taken a case. We have done a Markovnikov's rule. Now you can understand why is it that the secondary carbocation is more stable than the first carbocation. But this is not the only way. There are so many other ways I can tell you. I'm going to tell you, but before that, I have to look at the time. Take 30. Will I be able to take other things? I really don't think so. Right? Yeah. So I think we'll stop with this. Okay. Or I can give you a problem if you want. I have okay. So I have 1, 2, 3 molecules. Right. I wanted to arrange them in the order of stability. Go for it. This is a carbanion. So I have a chlorine atom. So I know chlorine atom is going to be an electron with the drawing group. So what do you think? Which is the most stable one?
Sir, is it the second, first, and then the third?
Yeah, second is the most stable, then first, then the third. Yes, correct. So the answer is 2, 1, and 3. This is the order of stability. Okay, now how? You want to explain, Kana? How is it?
Sir, because in the second one, the chlorine
Hmm.
atom is more closer towards the carbanion, and then in the first
Okay.
case, it's more farther than the second case, and then there's no electronegative atom.
Very good. Yes, that's the answer. Right. So it's all about where I'm going to have the least charge. Right. All of them have similar alkyl groups, but only thing is, one say in two of them, chlorine atom is there, which is an electron with the drawing group. Electron with the drawing group is going to decrease the negative charge. And third one, I don't have an electron with the drawing group. I have only electron donating group. So this is understood. Why third is the least stable? That we understood. Because there is no electron with the drawing group. So the amount of negative charge is highest here. Right. And if you look at 1 and 2, right, both of them have chlorine atom. Definitely the amount of positive is lesser compared to this case, right? But here you can see that the chlorine atom is 2 carbon atoms away, right? So, and in this case, the chlorine atom is just 1 carbon atom away. So I told you inductive effects are distance dependent, right? So obviously the distance between this and this is lesser. So this will have more effect on this, decreasing the negative charge. And in this case, it is going to have a lesser effect. So the amount of negative charge here is lesser than in this case. So this will be the order of stability. Okay. So anyways, we'll do a lot of such problems. Don't worry. So yeah, people, we'll wind up with this for today, right? So I think tomorrow, can I take, instead of 1.5 hours, can I take 2 hours? Is it okay for you? 10 to 12, can I take?
Yes, sir.
Yes, sir.
Okay, we'll see. We'll see what we can do, right? Because 2 hours continuously sitting for you will be very difficult. Like I can teach, definitely I can teach you continuously. But okay, we'll see what we can do. Maybe if I can have a break in between after 1 hour, if I give you 10 minutes, 15 minutes break, and then again I go for 1 hour, something like that we'll do. Right? Cool. Thank you, people. Bye bye. We'll see you again.
Thank
Thank
you,
you, sir.
sir.